This is the image I found on the Google Graphics. It was really helpful throughout my Calc 2 classes. Trig identities can feel unintuitive at the first glance, so I decided to make a video explaining in the easiest way, in my opinion, how to get all of them, with having to remember as little as possible. This is all you need to remember to be able to get all of the rest identities. Triangle-based definition of trig functions, Euler identity, and some basic algebra. Here we have every trig function and their triangle-based definition. You can pretty much get all of this just from the previous image, so we already have reciprocal identities out of the way. There isn't much to talk here. They are almost the definition for the secants, cosecants, and cotangent. What you need to remember here is sine, cosine, and tangent definition, and also that the cotangents is just an inverse of the tangent function, secants is just inverse of cos function, and cosecants is just inverse of the sine function. Now the quotient identities. We already know that the cotangent is an inverse of the tangent function, so what we need to prove is the first one. Sine and cos functions are in the form of something divided by the hypotenuse length. So if we divide one by the other, hypotenuse lengths will cancel each other out. So what we will left out with is tangent or cotangent. The Pythagorean identities are one of the easiest ones to prove. All you need to do is use Pythagorean theorem and divide both sides by a squared, b squared, and c squared to get all three of them. Already got the three of the boxes done, so now the sum identities. Those are one of the hardest and time consuming to get. The easiest way to remember them is by using Euler identity. All you need for that proof is Euler identity, some exponent rules, and also a complex number base. What we are going to do here is set the angle theta to be the sum of two angles A and B, and rewrite the whole identity in the form of single angles A and B. Do a complex multiplication. All we need to do is match real part of the equation and imaginary part. If you don't really understand what happened here, there is a video in the description explaining how this works. And that is how we got sine and cosine sum identities. For the tangent sum identity, we will use quotient identity. What we need to do here is multiply the top and bottom by 1 over cosine A, cosine B, so that everything will cancel out to the tangent functions. What we are really doing here is just multiplying by 1. For the double angle identity, we can use previous sum identities adding to the same angles. It is just really less general version of the sum identities. To get all three formulas for the double angle cos function, we need to use Pythagorean identities. For the next identity, you will need to understand what an even and odd functions are. Even functions are defined by this following equation, but what really means that the function is even is that the function is just symmetric around the y-axis for every point of the graph. The good examples of the functions like that would be functions of x raised to the even power, like x squared or x to the fourth power, or really any other function that is raised to the even power. Odd functions are similar to the even ones, and they are defined by this equation. The difference is they are not just symmetric around the y-axis, but also they are half of the graph, positive or negative, symmetric around the x-axis, which is the same as saying that the half of the graph is rotated around the origin by 180 degrees. An example of function like that would be x raised to the odd power, which is like any function of x or x cubed. So pretty much just by looking at the graph of the function, you can tell which ones are odd and which are even. Really only even function here is the cosine function and its inverse, which is seconds. All of the rest of the functions are odd. So this is why the following equations are true.